at the value of the neutron lifetime as a function of time. I think that this plot's quite popular. I'm just unfurling it kind of one step after another in a sense to breed a sense of drama. Okay. The point is, people go along, they do measurements, and you know that all these groups are feeling pretty good about each other. Okay. They felt like this is a nice, boring article that I'm going to get to publish saying, last person was right, last person was right, last person was right, until somebody comes along and says, no, actually, there's a problem. Okay. And then things jump, the error bars shrink, and it happened again. Right? This is a statement, I think, about humans and about how we do our business when we're trying to be honest and reasonable. So it's not enough to make the most accurate measurements. You have to keep in mind that we will view things in a historical context. I'll be the first one to admit that when I measured something that looks outrageous, I don't immediately jump to publication. I hold myself back. Perhaps I hold myself back long enough that the fiscal year ends, and then I'm on to the next project, right? That's what we do in applications lands, okay? And therefore, the results that are disparate from what you expected don't get published as readily as the one that comes along and says, la, 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 I'm doing exactly what the last measurement did. You got to acknowledge human nature. Now also, you have to understand all systematic errors. When you see clumps of data working like this, you know there's something that's going on of that sort. Okay? And often we don't understand all systematic errors. We can't devise experiments that are insensitive to all unregulated errors, and they're there. And we don't even necessarily understand them all. This isn't that we're bad people. We just don't know it all. So given this, how do we do data evaluation, that post-publication review process that I spoke of? Well, I call this slide nuclear evaluation in a nutshell. Step one, measurement is published. So, important point here. If it's not published, you don't enter the flow chart. Okay? So unpublished data never happened. Okay? You just hear rumors and mysterious mutterings in the back of the room that something might be different. Okay? Step two, the results are compiled. So when we publish our work, often, for example, we'll publish a paper. I do this myself all the time, that there'll be a plot of data and there won't be a table. Okay? So somebody has to at some point go out and get the actual values, put them together, do simple consistency checks, and put the data into a compilation of some sort. Step three, the data are evaluated. Now when you're doing this, this is where things require a lot of significant individual expertise. And this is an interesting point to note. Right now, data evaluation of the classes that we're used to using for application, for the most part, is not done by people who measure it. So that's, if you think about that for a moment, there's good and there's bad to this. On the good side, you've got people who are impartial. Their hands are clean, they don't come in with bias. On the bad side, they often don't know what's going on with uncertainties. They have to trust the veracity of the authors themselves. Now, of course, the paper was probably peer-reviewed before, but I will also be the first one to tell you right here that when I'm peer-reviewing a paper, I do not necessarily, I assume that people are honest for the most part, and that they're representing their errors in a realistic way. If I see something to disprove that, I'll question it. But a lot of systematic errors make it so that you don't see the problems. Okay? Again, honest people. Now, an interesting thing happens here. In low-energy nuclear physics, which is really what's applicable for applications, there's a branching that occurs. There are reactions, mostly cross-sections, for the production of specific particles and outputs as a function of angle, energy, etc. And this is in the Evaluated Nuclear Data File, or NDEF, database. Then there's structure, low-lying nuclear structure. That is in the Evaluated Nuclear Structure Data File, levels and gammas. And really, the people who do this work are completely separate from the people who do this work. At Brookhaven for the last few years, Mike Kerman, who's the head of the USNDP, has been trying to rectify that by having the two groups meet at the same time in what they call Nuclear Data Week. I kid you not, Leo can attest to this, he was there. All the reactions people are in one room, all the structure people are in another room. One time he tried to bring people together in the same room, and there was so much rumbling, there weren't even enough seats, nobody cared. So really, this is rather amazing from a human dynamics perspective. There's complete separation here between these two. But you might say, look, this is okay. This is the stuff that matters. And this is the stuff that people do because the Office of Science pays for them to do it and nobody else really cares. Right? All right, well, you could say that. And if you say that, then maybe you're not, so concerned, especially about that right-hand side. There's a few other problems, though, I do need to point out. Okay, right? Because MCMP, of course, is mostly drawing on the stuff on the left. There's a whole bunch of stuff in the middle, like thermal neutron capture gamma ray spectra, gammas following fission processes, okay? Inelastic scattering populating specific states, like the way that neutrons lose energies in matter, okay? Gammas from highly excited states, the states where the competition between particle and gamma ray emission are occurring, all the things that are the inputs into reaction. All of that lives in the middle, which means often it doesn't even have a formal evaluation process addressing it. There are huge chunks of the published data that we don't evaluate at all. And that's very dangerous. And so one of the things that we've been trying to address, specifically, you'll notice there's a common theme here, a lot of neutron stuff. Neutrons aren't very popular with the structure people. It's hard to do quality experiments with neutrons. The beams behave like cats, they wander everywhere. And for the application community, they care, but they tend not to want to go and do a lot of fundamental measurements. There is something of changing in that front right now with counterproliferation. So you begin to understand that this separation between structure and reaction is not very good when you think about how the stuff is actually generated, how these libraries are generated. So one thing that we see emerging from the way we generate these libraries is that there are a lot of compensating errors. So let's be clear about how NDEF is generated, the stuff that goes into the background in MCMP. We perform measurements, there's experiments. We then take a theory code package called Empire, for the most part. Okay? This is a code package that is maintained jointly by the US NDP and by the IAEA. It has the best physics of every type of reaction that we can come up with. Okay? This code package is used and moved around. Parameters are varied to reproduce experiment. That's how you get NDEF. What is in NDEF is a calculation tuned to reproduce experiment. The problem is you can't measure everything with arbitrary accuracy. That's why you have to do this. So I might measure the experiment with say a particle, I want to do d squared sigma d theta, okay, and I want energy bins that are, I don't know, it's a nuclear reactor, better than a kilovolt, like a 10 volts wide, and I want angle that's 10 degrees wide. Yeah, I'm not going to measure that for you. That's not going to really happen most of the time. So I'm going to have to calculate it. So you have to do this approach. So in order to try to rectify this problem, that we're having to generate things from a model, and we know that the model is not super reliable, we do this exercise called validation with integral benchmarks. And I'll show an example of one of these right now that I'm going to go to in greater detail, okay, which is this is a critical assembly. I think that that's actually a picture of Godiva. Later I'm going to show Jezebel. So this is a critical assembly, K effective of 1, of an actinide. Okay? And I'm going to compare my modeled results to the measured answers that I have here. And this is going to give me confidence that this process here, this combination of experiment and theory, worked. Okay? The problem with that picture is that when it doesn't, we come back here to the theory and we adjust the results again until it does. And anybody who does reactions evaluation will tell you exactly that. We adjust the theory until it reproduces the integral benchmark, not just the differential experiment, but the integral benchmark. They wouldn't stop otherwise. And all of this is because when you run NCMP, you don't want it to return an answer like, I don't know that cross-section, so I can't calculate your problem. And you don't want it to necessarily report back some subjective idea of an uncertainty. Okay? So we do this approach, and it has weaknesses. And I'm going to highlight one of those in a moment. Because you can't use integral benchmarks to gain confidence over your predictive capabilities if the theorists, the modelers, are using it too. It just becomes another experiment. You should take this and move it up here. It's just another kind of complicated experiment that you're using. So it's not giving you really, I guess what I have an issue with is the term validation. It is not validating anything. No more than this nice experiment, this is a picture of Vance, validated the theory. Okay, just another way of getting at things. Oh, and then afterwards, of course, you can perform a sensitivity study and go back and feed in yet again. But once again, there's this loop going around. Okay, there's no new information entering. So, part B, holes in the nuclear data. This is what happens when you ignore hidden compensating errors. Now, this is an example I got from Yasmina Buic from an apartment. Okay, we hadn't heard of before. For those of you who aren't familiar with this, the Maple reactors were reactors that were designed and built to produce medical isotopes using low enrichment uranium for the reactor core and a high enrichment uranium target. Okay? So this was done by AECL in Canada. They discovered that the reactor had a positive power coefficient of reactivity in June 2003. That was, this behavior, I love this line from the report, this behavior was deemed by the Canadian Nuclear Safety Commission to be a safety issue. So as this was said, they were ramping this thing up. It was supposed to run 10 megawatts thermal and 8 megawatts. They said, no, we're going to stop at this point. AECL engaged the services of a number of organizations, including Brookhaven, Idaho. INVAP is an Argentinian company, from 2005 to 2008 to identify the cause of the discrepancy, and the cause was never determined. And in 2008, AECL discontinued the project. Following this decision, AECL was served with a $1.6 billion lawsuit against, or should be for, breach of contract. So the bottom line is that the cause of the problem was never determined. But the inside scoop was that nuclear data might very well have been a potential candidate here. Do I know for sure it was? No. That's the problem with these sorts of things. You don't know what the uncertainties were. So this is a line that I heard from Rick Firestone, who's been my mentor in this. If you don't have good data, you'll make bad decisions. In this case, they actually built these things. So that's a bad decision. When it was sitting in design space, it wasn't a bad decision, although you still waste time and effort and money trying to design it. Okay, let me give you an example of how compensating errors can be introduced as an error, as an issue. This case study is the Jezebel critical assembly. So this is a critical assembly of plutonium-239. What I have up here is the evaluated value for plutonium and uranium 1.5 MeV. This is the prompt fission neutron spectrum that comes out of that process, as best as we understand. So we're doing a comparison between the experiment, what's measured, and the model, using two different databases. One is NDEF-B7-1. The other one is the BRC database that is used by CEA, by the DOE equivalent in France. So what I want you to do is remember the shape of that spectrum. That is a log plot on the y-axis, linear on the x. Okay, so fission neutrons are peaked up there below an MEV. They've got a tail going out. So where we're going to care about cross sections mostly isn't going to be way out here. It's going to be closer up towards the peak. Okay. So this was a neat little exercise that Eric Boge from CEA did. He went through one after another, and he replaced the cross-section set from NDEF-B7 with the BRC, and redid the calculation completely, just one cross-section at a time. And then he looked at the changes in the criticality in percent mil, thousandths of a percent critical. So in general, when people do this game, if it's under 100 PCM, they're pretty happy, 0.1%. If it's above 100 PCM, they start getting cranky and nervous. So let's start with N2N. So N2N, this reaction threshold's at high energy. And remember, there weren't a lot of neutrons at high energy. And so no great surprise, the difference is small. 14 PCM is, I would call, inconsequential. Okay? What's next? I just call it as expected. Well, you might think, what do you think would be the most important cross-section if we're dealing with a critical assembly? And what do you think? Fission. Fission's a good guess. 122 PCM. Okay, well, that's a little bit disconcerting, but given how incredibly important it is, I'd say overall that's not too bad. Small differences here gives you, 0.12%. Fortunately, this isn't U-235. The situation's better there. But PU-239, there's some people at the lab that I work at who care about that. Okay? All right, what would be next most important? Well, that's the cross-section to make fission occur. What about what you get out when it fissions? That's the fission multiplicity spectrum, and I would call 16 PCM good news. That's actually rather nice. That's pretty close to the same value. All right, how about capture? This is what's eating the neutrons. in the system. Now we swing positive, 275 ppm. That's actually a rather significant difference. I'd call that worrisome. Okay, the fact that it swung that much, this is over a 0.25% criticality swing by changing from one capture cross-section to another. Now, you might think that elastic and inelastic scattering, this is stuff that doesn't take neutrons directly out of the problem. They scatter them physically out of the problem spatially, but they're not eaten, they're not producing energy. That these would be fairly inconsequential. And you'd be wrong. In this case, they're huge effects. The good news is one swings positive, the other swings negative. Or I could say, the bad news is one swings positive and one swings negative. So the end, of course, when we go around the cycle, is that everyone says the exact same thing. I call that yikes, by the way. And that is that K effective is 1.00082 or 1.00060. Okay? But here's my question. Given this information, if you were designing a reactor that had plutonium in it, how confident do you feel? You shouldn't feel confident, okay? You can feel confident to design it. You shouldn't feel comfortable to build it, okay? Because that's the level of uncertainty that we have in this data that's underneath it. And this is plutonium. I would argue it's probably the nucleus about which we care second most in the world of applications. So compensating errors can mask bad data. So what is the source of the problem in neutron scattering? Well, here I have all of the databases that are currently used. Jeff, Jendal, Sendal, NDEF. These are Japanese, European, Chinese, okay? This is for the plutonium-239 NF and N gamma cross sections. There's definitely differences. Don't get too concerned about this over here. It's a question of whether somebody is averaging over resonances or adding them all together. Overall, not too bad. That's inelastic, okay? And that's the source of the problem. By the way, the elastic situation, of course, is also bad, okay? But that's why. There's an actual disagreement here. Now, you see all these bumps and wiggles and shapes. People care. They're trying to get this right. They're trying to figure out the physics of this problem, and they're having a hard time doing it. So why are these evaluations so different from one another? Well, that's because inelastic scattering sits in between that wall that I just spoke about. So I'm going to take an example here of iron 56. This is the evaluated cross-sections for inelastic scattering on neutron and iron 56 from several of those databases. But when you're down at this low-energy regime, low-energy neutrons, like where you would have from fission, you see all this up and down going on. That's because this nucleus actually has a bunch of discrete levels. And you cannot inelastically scatter off of a level that does not exist. To put it slightly differently, you better not scatter off of a level if that's not there in your code, okay? You will get an incorrect answer. So inelastic scattering lives between these two worlds. All of this structure is built into that rapid up and down that you see on the right-hand side. And where did it come from? NSDEF, that useless thing that nuclear structure physicists measure at the place like the 88-inch cyclotron or anywhere else, okay? That stuff that we write papers about weird quantum numbers. All of that is what's making that cross-section, because again, we turn the crank of the calculation to make this. And so NN prime for neutrons below 10 MeV is very sensitive to low-lying nuclear structure, and most of these cross-sections remain unmeasured. I've said that actually it's like the Roman god Janus, right? It's got eyes looking in both directions. It's both structure-dependent and reaction-dependent. So where do we go to get an answer to this? This is where we go back into the 70s show, the Baghdad Atlas. So this was by far the largest collection of NN prime gamma data that was ever taken. It was taken at the Al-Tuwaitha Nuclear Research Facility circa 1978. It actually ended in 1978 there, this particular research program. This is where it was located. There was an IRT 5000 reactor right in the center of this facility. It's a very nice data set. There was a beam line that was specifically designed. Unfortunately, that's the extent of the technical drawings that we have right now. Okay, with concrete, boron carbide, there's cadmium, all of this stuff to try to get rid of thermal capture, which is a big deal in a reactor. But they recorded not just gamma ray yields, but actually the gamma ray spectra. And they did this for a huge body of data. They measured for thousands of hours. They spoke about how they would measure for 1,000 hours and then anneal the detector and then do another one and have another one. They just kept doing this for thousands of hours to get this data set. And the same setup was used for all the measurements, which is great. That's consistency. They may have had systematic uncertainties. Well, we know they will have had systematic uncertainties, but they should all be the same, other than the stuff relating specifically to the targets. This is what the data looked like. This is what the front page looked like. There were 7,090 gamma rays observed from 105 targets and 75 elements. There were separated isotopes run for a handful of them. And the neat thing was that they normalized all of this back to one single gamma ray in iron 56. It was the first excited state to ground state transition at 847 kilovolts. And nice tables of data coming out like this. Really beautiful stuff, very carefully documented. So, unfortunately, the facility was decommissioned by the US Air Force in 1991. Just to be clear, this isn't the facility that the Israelis decommissioned. This is the one that we decommissioned in 91. So we actually blew up a reactor. We bombed a reactor. I think that's kind of cool. Sorry, a little strange, Dr. Strangelove moment. So, fortunately, there were a few copies of this atlas that remained, and Andrei Turkov from the IAEA had one, which he sent to Rick Firestone at the Isotopes Project at Lawrence Berkeley Lab, that he sent on to Brad Sleaford at Livermore, Aaron Hurst, and myself. Okay. So what did we do? The band group entered at this point, and the first thing we did was we scanned and used optical character recognition to enter all the data in. Okay. So now we have a spreadsheet database, and the data was then converted into an Excel spreadsheet, and we did normalization to the 847 keV line ourselves. So we checked for simple consistency. This is all just Excel. Okay, this was done, first part was done by Brad Sleaford, the latter part by Sean Walston. So also, once you have this, there's a neat thing that you can do. You can take this data, and using a code, a Python code called XLS to ends, you can translate it into ENSDEF format. And remember, until you get it into that format and get it compiled, it's not going to be part of our modeling effort to figure out what's going on. And this translation work is being performed by an undergrad in our department, Joe Labro. That's his charming picture from the roster photos. Now, in addition to the conversion to ENSDEF, which is how we would enter into the evaluation process, Aaron Hurst from LBNL has created a queryable SQL database of all the data that was in there. Okay? And the reason why is that actually the gamma rays coming out, in addition to being important for figuring out the cross sections, the gamma rays are very useful if you have an active interrogation system to determine if there's the presence of different material. So that this data in itself, it's not just useful in terms of figuring out cross sections, it's important to figure out if certain materials are present. So there is a graphical user interface that can be used to manipulate the data or execute SQL code. And all of the information from the atlas has been entered into this. So this is available. If anybody would like a copy of it, all of this stuff is available and open for dissemination. So I want to talk a little bit about why this was important. And it also highlights some of the earlier problems that I mentioned. Most of the data in the atlas, 42 out of the 75 nuclei, were never published in any form used in the evaluation process. I have here is going across the various, as a function of Z of the target, I have different years what publications were occurring. You should note, there's the atlas, okay? And this is the thing I put down at the bottom for here. If a tree falls in the forest and there's no one there to hear it, doesn't make any sound. Well, likewise, if your data is sitting somewhere and never published, did it ever really take place? Well, as far as the evaluation process, and therefore NDEF, and therefore MCNP is concerned, no, none of this ever happened. So why? Why wasn't any of this data entered in? That's a really important question. It's very important stuff, and it was never entered in. Well, actually, it's even worse than that. So some of the blame you could put on the Russians, right? This was Russians, okay? They didn't publish much, but they did publish some. This is an article from Physics of Atomic Nuclei. That's Yadrnia Physica after it started being translated into English. This was an article that was published in 2004 by the same person who was the first author of the atlas, Demidov. employing N prime gamma reactions to exclude nuclear levels erroneously introduced in other investigations on the 3- level in iron 56. And I want you to just look this abstract. In comparing the energy level and gamma ray transition diagrams obtained in investigating gamma rays from the inelastic scattering of fast reactor neutrons with the diagrams published in the last issues of nuclear data sheets, it was found that 120 levels and 34 nuclei must be excluded from compiled data because the gamma ray transitions expected from them were not observed. Now put yourself in the shoes of a nuclear structure evaluator producing 350-page A-chain documents after literally a year of effort of your life. This person comes along and publishes a paper and says you make a whole bunch of mistakes. You have to remove everything. How would you feel? To quote one of the evaluators recently, who I will not name, who I saw in April in Vienna, he said, "It's a bad paper." It's literally what he said, "It's a bad paper." He's a really good guy. Oh, but look, 6 years later, Nick Fodiatis, Ron Nelson, and Matt Devlin from Los Alamos come along, and this is literally the title of the paper, the first 3 excited state of iron 56. That's a real sleeper, okay? They say, look at that, level isn't right, okay? Look at that. Well, but now it's Los Alamos, and these folks say it in a nice way. They don't point out that there's a problem, okay? So maybe this is real. Let's look at a case and try to figure this out. This is a section from Demidov's paper in 2004. I'm going to look at one nucleus in particular. This is cadmium-110. It happens to have a lot of these levels that were excluded. That's why I chose it. It wasn't the most, but it was easy to show. So I've highlighted here in yellow the levels that Demidov said you need to exclude. So then I went to the latest issue of nuclear data sheets on this nucleus. And I've shown you where those levels are. They are there. He's saying they should be excluded. Now I want you to notice something here. Do you see here these things labeled XREF? This is where the data came from initially. What type of reaction produced this data? Do you see how there's only 2 letters, J and O? Okay, compare that to the levels above it. Lots of letters, meaning there are lots of different reactions that store these levels. Only 2 over there. Yeah, well, it gets worse. There's actually only 1. There were 2 papers by Pignanelli. Okay, they were PP prime and DD prime, not in coincidence with gamma rays. Okay, just particle singles measurements. These guys went in, they did their measurement, and they were really open in this paper. You read this paper, they published 2 papers, by the way. One was called hexadecapole strength, and the other one was quadrupole strength, but it was the same data. Okay, this is what it looks like in their papers. Okay, question mark, question mark. So it's not like the authors were lying. They knew that it was uncertain. In fact, in the text, what they were saying is that they cannot rule out these being contaminations in the target. And yet the levels stayed in. So structure evaluators hate removing levels, even when there is very little evidence of their existence. The result is that there are likely to be many spurious levels in NSDEF that could be skewing inelastic scattering cross-sections. This is the status that we have right now. Okay? Because people hate destroying. They always like creating things. Adding a level feels good. Removing a level, you better be safe and careful about it. Okay? Now, to be fair, the structure evaluator would say, look, I documented that there wasn't much here. Okay? But the reactions evaluators just take NSDEF as one big table and they run Empire. And that's how they generate the cross-sections. What is the effect? In this particular case, I went in and I removed those cross-sections using a cute little trick that Roberto Caponi taught me. If you ever get to a nuclear structure data file and you see spin 21, that means that some evaluator didn't believe it was real. They made 21 like blackjack. That's their way of making a comment on it. So when I made all those spins 21, they don't get populated then in the process. This is the change in the NN prime gamma cross-section. Obviously, there's nothing till you hit the first level. Okay? Then you start getting a bigger effect. It's about a 15% effect when you're at the end over here. So fission neutron spectrums. You can tell this is coming in around here. So this is clearly consequential. Oh, that's interesting. Okay, I decided it was time to end the talk. So what are we doing about this? Okay. We see that the first thing we're doing is we are processing the Atlas data. But in addition to that, okay, hopefully this will work this time, we're performing measurements. We can perform more modern measurements using our deuteron breakup capability at the 88-inch cyclotron. So the way we do this is that we send a deuteron beam from the cyclotron out to a breakup target. where we then get pulses of neutrons that go through a hole in the wall to caves 01 and 02, where we can do time-of-flight experiments. So we did one of these with an iron target right away. This was work that Leo had done a year ago. We can make a neutron spectrum that covers a fairly wide range of energies. At 16 MeV, we get something that doesn't look all that different from fission. At 44 MeV, it's a significantly harder spectrum. There's a wonderful story about how we actually got these shapes, but we measured them at Berkeley by a double time-of-flight approach that Josh Brown, another student in the department, pioneered. And I say this, our student-led experimental program is led by Josh Brown, Leo Kirsch, and Keegan Herrick, who's an undergrad here. And we have similar measurements that are taking place right now that we're partnering with people in Dresden and at Galena. So let me give you an example of one of these. This was that first experiment that Leo played with, okay? And we're looking at the ratio of 2 gamma rays, what we measured in this experiment, divided by the value from n-depth. And what you see is, one of these things, the ratio is quite far off of 1. And that's because I've got this level. The one that has that 2229 keV coming out of it on the right, okay? You subtract that level, and everything gets better. This is more evidence that that 3- level in iron is gone. It's not real. It was a mistake. I would hypothesize that 2229 is very close to the gamma ray that we would see from neutron capture on hydrogen, and this is probably where it came from initially, but I don't know. So more recently, we've started an effort to analyze data from what I would call the mother of all iron-56 data sets. This was taken using the Gratina detector at Argonne for iron-56 pp prime gamma. So this is work. This is how the experiment took place. We send a proton in, it scatters off the target, leaving it excited. This nucleus then decays by gamma ray emission, which we detect. We detect the particle with its energy in these phosphorus particle detectors. And then we have a cascade of gamma rays going through a gamma ray detector, which is part of the Gratina array. So, but these detectors are electrically segmented. Here's 3 of them put together. They're electrically segmented, which allow us to add back all of the energy components that we had from the experiment. Okay? When you do that, you get to remove a whole bunch of the Compton background, and I have these examples of what the gamma-gamma spectra look like before we turn the gamma ray tracking capability on, and afterwards. You can see how much brighter the correlations are. This was an incredibly successful experiment. Everything worked precisely as designed. I'm very excited about this because Gratina was not built to do this. It was built to do basic science. But here it is showing its utility for an important application. And really, you need good structure data in order to properly model an N prime gamma. I should point out again, we need unsegmented detectors as well. So there's Leo, okay? So we also have a local capability, which is going to allow us to drive down some of these uncertainties in an energy that's important. And that is the high flux neutron generator on campus. So Leo, you can take these slides, the ones with a pretty picture of you or whatever in there, when you use it. All of these slides you're about to see come from Leo. So he is completely over the line when it comes to animation, and that's coming from me.
Corey, I think Corey might have first.
Yeah, this is, all right, if you guys haven't seen this, get ready. This is like a Disney film, okay? So how does this work, okay? You put deuterium gas. Corey, are you responsible?
Maybe.
Yeah. Okay, you put deuterium gas into these ion sources. Okay, there's the gas, and wait for this. We pump in RF. Bing, 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 bing. Okay. Isn't that cool? Then the gas becomes ionized. Some of it does. And in this archaic picture, there are 500 plus holes on either side that you can extract ions from. We now have it down to one elegant hole, a bit bigger, we just heard about. And you can extract the ions. Okay, charge up, oh, it gets better. Okay, you can extract the ions by making the target negative 125 kilovolts. There are lots of interesting problems with this that Corey or Leo or Carl can tell you about over beer or maybe whiskey. It's hard to do, okay, but they have managed to get this thing to work in a stable configuration. You do DD fusion. Everyone knows neutrons are blue balls, they shoot out. Okay, you have to flow a lot of water through this thing because we are talking about a lot of heat. And this whole thing lives in the middle of our vault, the old sampler radiation vault that looked in at the trigger reactor. It sits often off to the side, but without much problem, thanks to Leo, you can slide it on a frame right back over into line with the target. That's a picture of it on. Not with the target, but with this port, this straight port. where you can send the beam out to a cage. This was a conceptual cage, it is now a real cage. And then here's Ed's accelerator down this end over here. It's a monoenergetic beam, 10 to the 4 to 10 to the 6 neutrons per second per centimeter squared. How about 4 to 5, actually? 6 was what the design parameter was, it's not going to get there. Okay? And we also have a rabbit, which allows you to send samples back and forth in less than 1 second. Okay? And so you can do irradiation and look at activities right after. This is like your fishing line experiment, Rick, except even faster. They had 2.45. Okay?
Which was just as fast.
1 second. 1 second. You could shuttle back and forth. You could pull out. I don't think you could throw it back in again, right?
Not in a second.
Okay. You gotta get Howard trained faster to do that. Okay. There's also a poly shield that you can put around for thermal operations. And you can then, we commissioned it last July, and we measured indium activation. There's something to point out about this. If you're sitting in this outside world, this is the spectrum that you see. And as finally the nuclear engineering effort has pulled me over to the realm of using lethargy. This is neutrons per centimeter squared per second per unit lethargy. There's the 2.45 MeV peak. The blue is what you see if you're in line with that beam port. The red is if you move it off to the side. The 2.45s go away. That's what 2 millimeters of cadmium does. Gets rid of the low energy thermal bump. That's what that bump is, of course, that's thermal. Okay, so it is a really pure 2.45 MeV neutron source. This is what it looks like now with Corey, as his chest is a target. That's our real neutron source. And that's our local experimental capability. So I'm almost done, it's 4:57. I will say this, that everything that we're doing here in the nuclear engineering department at LBNL is part of an effort that we've had where we're trying to take a leading role in coordinating the applied side of nuclear data activities in the US. So we're focusing more on the application because this program is resident in the nuclear engineering department. So part of this effort was that we held a workshop in Berkeley from May 27th to 29th called Nuclear Data Needs and Capabilities for Applications. We have a white paper which has been in limited distribution to the people who presented at that workshop, and probably sometime in the next week or two will be made commonly available. It includes a matrix of every nuclear data need that we found both at the workshop and in 5 major other white papers that have come out. And it co-indexes them between their application space being national security, meaning the defense programs, counterproliferation and safeguards, which really is at this point now its own separate program. That would include forensics, by the way, in that area. Nuclear energy, and medical isotope production. This is the conference photo that we had, and the front cover of the white paper. Anybody who's interested, I'd be happy to distribute a copy when we get to the final version of this thing. We are going back and forth between all the authors, but we're now getting very close. We're at about 90% completion. There are also complementary activities in basic nuclear science and medical isotope production, in addition to all of the work that I've been talking about, which has mostly an application centric for national security. So with that, I'll stop with 2 things. I'm going to come back to the collaborators, but I'm going to do a quick blatant advertisement. We're going to be having discussions of the roles of nuclear data in 2 sessions. One is one that Lee Schroeder took the lead in organizing at the APS meeting, and another, there'll be a panel discussion at the ANS meeting in Washington. And I'll go back here and leave us on the list of all people who collaborated. Thank you.
Brilliant, and it was a delight to see the role that our students are playing, including our undergraduate students here.
Absolutely.
Keaton did the rabbit. Keaton and Jody there.
Working for you, right? I think it was Leo's rabbit, but those guys did a lot of it. Yes.
Questions?
With your database approach to the Baghdad data, do you have dates from the last anneal available?
The question
If they had to anneal every 6 months, there must have been a reason.
Oh, absolutely. No, in fact, they annealed, they were scrupulous. They listed they annealed every 1,000 hours of runtime. So what they did was, they don't even, unfortunately, there are certain things missing. They don't tell us, for example, did they anneal and while they were annealing run another detector? They don't say that, okay? Or did they just take the whole system offline, anneal, bring it back and run again? They did mention that when they did the anneals, they went back and ran certain calibration sets, again, to make sure that things were working properly, that the efficiency was remaining constant. One of the big ones there is iron, because everything's going back to that one gamma ray. By the way, that one gamma ray has got a problem. The NP reaction in iron 56 makes manganese 56, that beta decays right back into that level. They were unaware of that. Okay? There's another paper by Bayer that was unaware of this, and we now confirmed this. Okay? When you pointed it out, they realized it. It works out to actually being, in this case, for this data, fortunately, there are a few high energy neutrons here. It's about a 6% effect. But they do not have detailed logs about stuff like that. It was a paper. They have about, I think it's a 22-page preface, which is all the information they had about the experiment. There is one important thing to note that they do have as well. Because they ran natural targets, in the case of the iron, for example, they had iron 54 and 56 present in the target, and we were able to look at the yields of the 2 to 0 and the 4 to 2. These levels are at higher energies in 54 than 56, and so we can use it to confirm their guess of the shape of the spectrum as a function of energy. So we have that, and that seems to be good. Okay. It's remarkable what they did. They did that, the shape guess was done by application.
And this is lithium drifting, okay?
Yes.
And they're annealing themselves and redrifting and all that stuff.
They absolutely were. This was 78 was when it was published. So the data was taken in the years preceding 78. Okay, they also unfortunately do not tell us what that was. The detector was a 15% detector.
Lee, what was the point of this program? What were they trying to accomplish? Was it a joint Russian-Iraqi?
Yes, it was a joint Russian-Iraqi program. You asked what they said. It was important to determine statistical model parameters. I think actually at some level, frankly, it was cover for other activities that were going on. But I'm glad it was good cover. This was great. This was really good data. No, I mean, it's amazing what they did, but it was not, I don't think this was, they had a great yen in their heart for this.
Further questions? By the way, part of this renaissance of nuclear data, this is, there's a lot of opportunities now, and I think one of the things in Lee's proposal here for the West Coast Data Center was not only to keep in play the emeritus evaluators, but also to train a whole new cadre into the joy and magic of nuclear data. And I think you've conveyed that very nicely. So if you get excited by this, come talk with me.
We really are. That is why the USNDP wanted this here, in part, because it is a university. And because also you folks being in the nuclear engineering department actually care about applications. So a lot of this stuff, we were capable of doing these measurements back in the 70s and 80s, and we were doing some of it. We stopped very prematurely. We measured very little of what was needed, and we moved on. And so really, the nuclear data, both the production of it by measurement and then the evaluation of it, we want to see more of that stuff linked in the same person. So somebody who understands both sides of this problem, not just a person who never measured a single thing evaluating, and a person who never evaluated at all and thought about those systematic uncertainties, measuring it. So we want to try and breach that gap and have people thinking about both sides.
Other questions?
Are there any of the Iraqi or the Russians still alive that you go back to talk to?
Very good question. So Demidov, okay, we had a student here last year, Ivana Abramovich, and she is going to come back here. She's from Eindhoven. She's Serbian. We had Ivana write a very respectful and culturally consistent letter to Demidov and Govor. And Professor Vujic vetted it and said, very good, okay? There were no answers from them. Okay? So unfortunately, they would be quite old at this point, but Demidov did publish a paper in 2012, or at least he's on a paper. I don't know what that means precisely. He was not the first author, okay? By the way, when you look over there, we're trying to go further back from that. All the Iraqis, Ahmed was the lead author. No evidence that they're in the field or perhaps even alive anymore. In fact, one of them I think might have been there at the attack, so that probably wouldn't do well. You can watch these people's careers over time. You watch students emerge in their papers and then go away as they finish their careers and move on. It's very kind of, I don't know, captivating watching this happen in somebody's career. So we have thought about reaching out to try to speak to some of the other folks who collaborated with them. And so if you do know any Russian nuclear physicists who might have been in Iraq in the 70s, please let us know. We're trying to reconstruct what was going on there.
We should go compare databases and see if any of them were our alumni here.
Good question. I don't know. Most of the names, you look at the names, it's pretty clear that these were Russians.
Right.
And
mostly Russians.
And they really, unfortunately, they published their data in a conference proceeding that nobody has a copy of some conference that took place like in Kazakhstan. Okay? I mean, there's just, you know, the IAEA didn't even have this stuff, and they keep pretty comprehensive records. So really, it's lucky that this thing survived, that there were a few hard copies. It's like CSI.
Great. Let's thank our speaker.